continuing with section 1.3. So we stopped here. So let's look at what we mean by span of a certain number of vectors. So we have, let's say, p vectors. So now and they are in Rn. So Rn, remember, means there are n copies of R. So we have seen R, R2 and R3. So this is a number line, this is a plane, this gives us a space, and then the rest of them we cannot imagine or we cannot visualize, but you can just see an extension of these R's. So if our vectors lie in R sub Rn, then it means each vector will have n components or n numbers in it. And then, but the number of vectors is p, and p could be different from n or same as n. So we say that the set of all linear, if the set of all linear combinations of these vectors is denoted by span v of these vectors. So the span v1 up to vp is the set of all the linear combinations of these vectors. So for example, if you have two vectors, u and v, then span of u and v what will that be? That will be the set of all the linear combinations of these vectors. So that is what the set is. So how can we see it geometrically? Well, in R3, span of a single vector, or span v, that's how we write it, is the line in space containing the vector v and the vector 0. And span of u, v, span of two vectors in the plane in R3 contains u and v along with 0. So here is a geometric description of the span in R3, and then we will see this span in R2 as well. So here, so if we have only the v vector, then all the linear combinations of v vectors, so if this is the v, the linear combination, well, there is no other vector, so we cannot combine it with another one. We can combine it with itself. So, for example, we can have a 2v. This is being counted from here up till here, that is 2v. And then we can have a minus v. We can have a 3/2 v or 1/2 v, which will be like this much. So these type of, so if you notice where are they lying? They are lying on the line through v and the origin. So that's what we get. We get a straight, just a single line. But when we have two vectors in R3 in the space, so here are the two vectors, one is the u vector, another is the v vector. So then we get a plane which contains the u and the v vectors. So that's what we get in R3. What about in R2? Well, if again we have a single vector, if we have a one vector in R2, then the span of that vector will be again a straight line through the plane. So again it will be the line joining the origin and the tip of the vector, and then it will be the span of that single vector will be a line. Now what about if we have two vectors in R2? Well, if they are not multiple of each other, then you remember that will be span of one vector. But if we have two vectors which are not multiple of each other, then actually they give us R2. So they will span R2. So for example here, so this is our usual vector, the usual system, coordinate system. But now if U is here, like I showed it with the red line, and V is the blue vector, then we can create these grids parallel to, drawing lines parallel to the V and the U. So now we are talking about V axis and U axis. So we don't have our usual X, Y axis or X1, X2 axis. But now U and V may not be perpendicular to each other, but so this is how, so one unit is V in this direction, and one unit in the other direction is U. So this is one U. So if a vector is over here, so you can think of it, how will I tell what is or how can I express this vector in terms of the U and the V? Let's call it A. Then you may notice that A is equal to, so I can reach A by going up till here and going here and then going up. So how many units of V we travel? 2V and then plus 2U. Now if I have a vector somewhere, let's say over here, so then how will I find the coordinate, the linear combination of that, or how can I write B in terms of U and V? Well, we always start from the origin. So starting from the origin, if I can go 3U, so 1, 2, 3U, so B is equal to 3U, and then I have to go in this direction. So 3U minus half B, V, because we are going the opposite direction of V. So this is how you can, given any vector in this plane, we can write it as a linear combination of U and V. So which means U and V span this whole plane, which is R2. Okay, going further, now we have the examples to solve. So remember that example that we left up there. So now we are going to solve it. And so basically, you notice it says determine whether B can be written as a linear combination of A1 and A2. So what does that mean? It means we are trying to find if this has a solution. So we are trying to find if the equation x1 A1 plus x2 A2. So if this has a solution. So solving this or finding the solution of this vector means basically just solving using the augmented matrix. And I augment this B here. So I have to make these two quantities 0. So I will say 2R1 plus R2 and then 5R1 plus R3, and I get, so the first row is not changed, so I'll write it as it is. Second row, this becomes 0, so 2 times 2 is 4, 4 plus 5 is 9, 2 times 7 is 14, 14 plus 4 is 18, and then here I get 0. Next row, we are multiplying by 5, so 10 plus 6, 16, and then 5 times 7 is 32, 32 35. 35 minus 3 is 32. Okay, so next thing now, so this was my pivot. Now I have to make this the pivot. So I divide by 9, or I multiply row 2 by 1 over 9. And let's, because we can easily do the multiplication by 1 over 16 of R3. So the first row is not changing, but the second row becomes, and the third row. So next step is to make this quantity a 0. And also I will need to make this quantity a 0 as well. So I multiply the second row by -2 and add in the first row. Then for the third row, I will multiply the second row by -1 and add in the third row. So we end up getting, so remember now second row is not changing. First row will change. We have a 1 here in the first row, and this quantity is going to become 0. What happens to the top one? So I multiplied this by 2 and then added in the -2 and added in the 7, so I get 3. And then the last row gives me, so which implies that my x1 is 3 and x2 is 2. So now I can say yes, B can be written as a linear combination of A1 and A2. So B is equal to 3A1 plus 2A2. Next example, so again same thing, can be written as a linear combination, but now we have 3 vectors, so it should say A1, A2 and A3. We have 3, A1, A2, A3. Okay, so we do the same thing. So we want x1. We actually are solving this equation, this vector equation. Take the augmented matrix. So the first thing I do is make the -2, 0 in the second row, sorry. First entry in the second row, I have to make this a 0. So I do 2 times R1 plus R2. First and the third rows remain the same. second row is changed, so I get 0 here, 1 here, 4 here, and 3 here. Now I have to make this 2 a 0. I use the second row. I'll multiply the second row by -2 and add in the third row. Okay, I think I will move to the next line. I don't have space. Okay. So first row is not changing. Second row is not changing. So this gives me 0 here, 0 here, 0 here, and 0 here. So what does that mean? It means we have a free variable. So note that x3 is free. We can write the equation as x1 plus 5x3 equals 2, and x2 plus 4x3 equals 3. Now we will say let x3 equal to t. Then x1 will be 2 minus 5x3 from here, but x3 is t, so that is my x1. What about x2? It will be 3 minus 4x3 or 3 minus 4t. So let me rewrite the x3 over here. So these are the values of x1, x2, x3. So what does that mean? It means we can actually write B as many different linear combinations of these three vectors. For example, if t is 1, then x1 will be -3, x2 will be, okay, let's do it like this. Therefore, B can be written as -3a1 minus a2 plus a3. Now, if you give t another value, you can see that you will get another linear combination. Okay, last example here. It says determine the values of k for which the vector y is in span AB. So what do we mean by a vector being in span AB? Basically the same thing as we have seen before. So we want to see that the system of equations x1a plus x2b is equal to y, which means we have to solve the augmented matrix. So again, we make the -2 0. This quantity we may want to make it 0. So multiply the first row by 2 and add in the third row. So the third row becomes 0, 2, and over here I have 2k minus 3. Okay, so next step is to make this quantity a 0. For that, I can use my second row. I have to use the second row. Multiply it by -2, add in row 3. So row 1 is not changing, so I can write it as it is. Row 2 is not changing, but row 3 is changing. So we are multiplying the second row by -2. So this gives me -2 times -5 is 10. So 10 plus 2k minus 3. 10 plus 2k minus 3. So which gives me 2k minus plus 7. So now if you recall, this third row, if you look at it, it's saying 0 is equal to 2k plus 7. Now if 2k is not, if the value of k is such that this quantity is not 0, then there will be no solution. So we want it to have a solution, so that we say that the y is can be written as a linear combination of AB. In other words, so that y is in the span of AB. So in order for it to be in the span of AB, we must have, for y to be in span AB, we must have 2k minus plus 7 is equal to 0, which gives us k is equal to -7/2. So that's it. We'll now go to section 1.4.